on how to build scalable AI systems. So this presentation is mostly about the learnings we had while we are doing it internally, and then the tools and tricks of the trade, and some of the do's and don'ts, and the models and the architecture we had used internally. It's not necessarily completely internal to our company or anything. It's going to be much more generic than that. Hopefully, the story is that we'll first go through the challenges, and then we'll try to go through the architectures we used, and then all the incident, the tricks of the trade, and the architecture descriptions and everything. So let's start. Okay. So let's first discuss on how to why scalability is like really critical for AI, since the talk is building scalable systems. Uh, like these days we see like uh, huge workloads both on data center and edge, whether it's your on-device personalization, server-side inference. Scalability underpins everything. Reliability, responsiveness, we want everything. We should be able to handle busty traffic, evaluating model sizes, strict SLAs. So performance engineering isn't just a luxury, like it's foundational. We want it to be at the center of our design. Scalability ensures our models deliver consistent user experiences, no matter the device or region. Especially when we are trying to implement inference pipeline that must support spikes during product launches, global events. Our infra should scale like really fast, recover really quickly, and preserve privacy. We'll walk through how to achieve this by integrating cloud native patterns and hardware aware design. So now within this, let's try to see what are the even more critical requirements. We'll try to keep this as much as infra focused. Uh, this is not like more about modeling or something. It's very much about infra. Okay. So now, like uh, these are the main requirements we have. We want compute elasticity, resilient data pipelines, versioning governance, low latency inference, and cost-aware design. So let's talk about the first point, compute elasticity. So, uh, like, we want it to be as scalable as possible and as elastic as possible. What I mean that is like we should be using something like elastic k8-based compute, or basically anything that where you can it's elastic enough and then scalable enough to handle the loads. So uh, like we kind of use some version of k8-based compute. It tightly integrates with our event-driven pipelines, supports model governance with metadata tracking and everything. So the next point is resilient data pipelines. So we want something uh, where there is no like which can handle like single point failures or any sort of network errors or anything like that. We don't want one error in like say Kafka or Redis, like that shouldn't affect the model's accuracy. We want pipelines that are resilient enough to handle all of that. And governance. So like this is one of the most important parts, especially when it comes to security or like even like just ensuring the reliability. We don't want any experimental model that goes without live checks. We want versioning where possible, and we do this with metadata tracking, auditing. We have metadata like versioned everywhere. We can go back to previous versions, come back later, everything. And then the next one is low latency inference. Low latency inference is our North Star most of the times. Like we want sub like 100 milliseconds response time generally. So we want our SLOs to be like really tight, and this is one of the main requirements we have. And then finally, cost aware design. We know these GPUs, these compute, they don't come cheap. We want cost awareness so as to prevent runaway spending. We operate with usage quotas, like per team, per user, per groups, and we want enough observability tooling that will help us track all of this. Next, so let's go into each of these like in more detail. So scalability patterns in like AI workloads. Um, so one of the things, like if you can ignore this whole presentation, just remember this one thing. Just make it everything really modular, really hybrid, and really distributed. So we want a hybrid version of compute for everything. Like I'll go why in each of these cases. Like so, especially with given the cost and everything, we want to have something like horizontal scaling for inference. Anywhere inference is involved, you don't need like a really huge high memory GPU nodes. Those are like really costly for inference, for inference. And where you do need them is vertical scaling, like is like for training time. When you are trying to like for training compute, we want vertical scaling. We want as high memory GPU nodes as possible. I mean, these go in your like really high memory A8 one and A100s and all that stuff. And so horizontal scaling is especially crucial for anything, any services that go like recommendations, anywhere where QPS can surge like unpredictably. You want horizontal scaling, right? Like you want like something that's like really elastic. You can very cheap nodes you can assign to them. And vertical scaling, especially like you can have something like these days LLMs, they run like I don't know like 100 GB in weights or something like. So you want like really like powerful nodes there. So our clusters typically have like mixed training workloads, like, and then they're like RDMA aware schedulers. They integrate with seamlessly with on-prem and cloud GPUs. Checkpoints like is one thing that like checkpointing, it allows us to aggressively preempt like spot nodes, dataless. I mean, basically like anywhere like you want spot nodes and stuff. Yeah, so like try to use like as it as distributed as possible. Like we do use like lots of PyTorch, and then Ray, and then of those kind. And so now spot ephemeral instances and checkpoint resume training. This has been something of a like boon to us. So especially with the other things like this will come next. Okay. So we know, like, okay, now we have covered the compute part of the thing, the compute part. Now let's look at the data ingestion and the pipelines part. So data is lifeblood of AI. We all know that. So like most of the cases, we ingest data from various sources, including servers, sensors, vendors, internal logs, I don't know, like external streams. So like data is like really important. So, like, I mean, you can like split it into two of them. I mean, like one of them is batch, one of them is stream. So for batch, like we should use something like, I mean, anything that goes in terms of like the Apache Spark, and then like you can have something for Airflow, and then iceberg tables. So we like, I mean, we internally like rely heavily on like Spark for and transformations, and then everything is being coordinated by Airflow DAGs. So like, I mean, your mileage may vary, but like this is the typical flow for most of the like this is the pretty standard flow. So the data logs, the data lakes are built on iceberg tables. So we can have like some sort of like snapshot isolation, and then time trial for reproducibility. You want to come back, you want to go, that kind of stuff. But like for something more real time, like say for anything like real time predictions, I'll let you think of the use cases. But like so anything where real time predictions are involved, we can we can use something like Kafka to stream everything, and then we have Flink based jobs to enrich features. And then these features, you can basically store them in like Redis instances or like ScyllaDB, I mean, or any of that sort. And then, streaming and batch, like, I mean, these should cover most of our needs. Like, and then, like, we don't like GPUs basically. GPUs are used to accelerate dense numerical feature generation at the runtime. So and then you can even offload some of it for like real-time enrichment. Next, let's look at the training part of things. So we talked about the compute, I mean, and basically, and then we talked about the data ingestion pipelines. Now let's talk about how the infrastructure is there. I mean, how the typical model training infrastructure looks. So we have like specialized GPU clusters. These are like multi-region cross availability zones, or like this can be like something like AWS for for generic cases as well. So you can have anything multi-region cross availability zones. So this should serve most of your users' requests wherever they are, without much of latency issues or anything like that. And then we all the training jobs write checkpoints to S3 compatible blob storage, so which are like very snowball ready. And for portable workloads, we even package them with snowball to offline edge locations. And then we have like RDMA over converged Ethernet. Like it's for like fast inter GPU communication within a rack, and then TCP fallback if cross rack bandwidth drops. Like, I mean, in case that's an issue, like you can just go back to good old TCP. Next, so and as far as the orchestration is considered, like if we can go with something like Argo CD, like this is pretty open source, and then like you have custom controllers. You can basically write like very rule based controllers and everything like that. So so we try to have like advanced scheduling policies, like priority preemption, and then where you need like something allocated based on priority, and then gang scheduling for job stages, like where if you want like a group of job stages to be together, and then cost based optimization. So cost, we have to consider cost here as well. So depending on the cost, you can write like custom rules. Again, this depends like heavily on the actual infrastructure and the actual compute you have. So make sure to write custom controllers for that. So our training platform, so the training platform basically should also integrate seamlessly with telemetry from GPU stage, IO stats, job health, and provide and which allows proactive throttling or rebalance. So this is the typical model deployment architecture. You have something like ingress, and then where it goes to service mesh, and then it goes to model pod, and then that essentially gets the features from Redis and then server side. So let's go deeper into each of these. Like, I mean, just to see. So all of these are like Kubernetes native. Let me cover one thing like before going to the next slide. So all of this is K8s native, or any of your like orchestrator native. You can have like Terraform or whatever, and then each like basically this is the typical one. Like everything has a Istio in it. It handles routings, retries, MTLS, everything like that. And then they have internal APIs registered in a service mesh. And then it should support scaling based on both CPU and GPU utilization. This is essential. Uh, yeah, so let's go to the deployment architecture in more detail. So we have a canary and then shadow traffic via flagger and then envoy filters. So basically we try to do canary deployments and then we test with a little bit of shadow flagger, and then we have flagger to adjust or revert or anything like that. And we do have specific envoy filters. Next, model uh, like versions are tracked in our internal registry with approval workflows. This is basically to ensure that nothing goes out of hand or anything like that. And then batch inference, it's triggered by like event-driven pipelines. Like this can be done through Argo or any of your TravCA or anything like that. So we don't like necessarily treat model deployment all of it as like one task. So we should treat it like as rigorously as software engineering. It's not just that uh, like it's just one time set and forget. You want to like tune it over time, and then like the same rigor should be applied here as much as you do on your the software engineering part of it. So MLOps pipeline should follow strict CI/CD patterns. Like whenever like, this is your typical someone pushes to Git, it gets a Jenkins build, and then you get like GPU based training, evaluation, and then validate metrics, and then you come back. Once model passes evaluation, again it like you can go to internal registry, and then you can use like then it goes to your typical Helm and then Terraform or whatever, and then it gets deployed. So all the future store versions or use like something like delta checkpoints. This gives like a full lineage from like raw data to production inference, everything you should have. Next, so drift detection is key. Basically, like so we should compare something like live inference distributions with training valid distributions, and then alerts are routed through the typical Grafana, Prometheus, and like the hence. Okay, let's go to the ML pipelines in more detail. Like I think we have covered most of this. Um, yeah, so this is like I said, typical Git flow, and then Git to Jenkins, and then you go to GPU, and then evaluation side, and then push, and then yeah, I think we covered most of this. So let's go to performance optimization strategies. Like how that would help us. Um, so one thing we can do is that before that, let me cover a few things. So optimizing AI models for performance, how would you go about that? So it has to be like a multi-layered effort. Uh, we can leverage like the tensor cores wherever they are, and then like wherever they are, and then used like mixed precision. That way you can basically cut memory footprint and then increase throughput significantly, sometimes even like 2 into 3x or something like that. And we can convert everything into like ONXS or core ML forwards formats, and then quantization definitely helps. Model size, that's there, and then we can also prune layers and then like fuse operations wherever possible. On the server side, we can like monitor GPU utilization with like cube state metrics, custom exporters, and then this help us like essentially identify bottlenecks, underutilized memory if you have something like overcommitted inference queues, poorly packed pads, and then auto scaling parameters. Optimization again like it's not a one-time thing; it's a continuous loop. Like we should profile tune, validate, and things like that. Yeah, these are some of the things I talked about earlier, like performance optimization strategies. Like, let's go a little bit like into some of the other aspects of it. So one of the things we want to optimize for is cost. Um, Cost is something like really crucial here, especially when dealing with AI infrastructure. So one way to do this is like have an internal autoscaler, and then you can like that determines in real time whether to allocate jobs for either is it like reserve nodes or stability, like reserve nodes like basically for stability, and then spot nodes for cost savings. So you can basically like try to have an internal autoscaler plugin. That way you can have like a reasonable cost effectiveness. And we can back this with checkpointing and retry logic to tolerate any preemptions. So, and then GPU sharing is one thing where it really helps. Like, so there are like these days many multimodal pods with Triton. Like, so that way you can essentially use the same GPU for many things. This essentially like improves our utilization for models that are like really small or sporadic load, or and then SLO aware inference queues enforce timeouts dynamically. Like, I mean, you don't need to like really worry about that part. And then like so anything like if you want like really SLO aware, you can have it through our dynamic allocation of this, and then you can basically put like something like very low priority or something almost bordering on batch. You can uh, drop them and then like just like batch them for later. Also, one thing that really helps is like have like real time metrics for everything, like for all the cost dashboards. That way, you can sort of like track uh, what's the cost like live, and like have them like per team per model, and then like you can have like more detailed view in terms of like GPUs, storage costs, and even like amortized engineering time per deployment. Like basically have it as granular as possible. That way we want to like look at every dollar spent, and that's like just like when you want to be able to justify that to your stakeholders. So think we're running a little late of time, so let's go through the next ones really quickly. So this is like very simplified view of like one of the like basic cloud native AI systems. Clients basically interact with the API gateway and then issue mesh, and then it goes to our the API gateway essentially performs all your rate limiting. Like this really helps. It handles the authentication, and even the request shaping, like if something needs to be done. And then you have a HTONS mesh to route traffic like intelligently, balancing between like replicas based on latency and health scores. So each inference powered, again, you should optimize to whichever hardware you're using. We like, I mean, if it's a training server, like you want to have like one or more models, like depending on traffic patterns and resource constraints. Next, features are pulled from like again like a model registry, pre-populated via real-time enrichment jobs as discussed. Next, so all of them, you should be monitoring all of them, like using Open Telemetry, Prometheus, Grafana, wherever it's needed. And we should essentially have like logs. Like again, this flow can be varied. Like your mileage may vary, like something like fluent bit, and then to locate through S3 path for like cost effective, and then complaints. So like this essentially gives like a really tight feedback loop between live traffic, infra usage. Like you see that we are measuring it at every level. So you can always, it's pretty modular, very observable, and very horizontal scalable. We don't have any component that's like very fixed here. So this is like a pretty simplified version. Like, I mean, you can like modify it to your needs. So this is again your typical cloud native architecture. You have the training jobs, you have the feature store, the distributed training, and then the model deployment stack. This typically it looks like this to us. So everything on the right is like basically data ingestion, training, and then the models. This is some of the more advanced like topics. So like we want something like at least at the scale, we want models performing well across geographies, users, and workloads. So for something like LLMs, use token parallelism and then deploy in multi-region. So this really helps. And that way, each GPU handles a portion of the token sequence, which allows latency to scale sublinearly with model size. So again, this also helps with like fault tolerance, and then you can reroute requests if you need that or anything like that. Prompt caching is one of those things that's like really useful. So like instead of like just cache prompts using semantic hashing, and instead of using exact matches, like compute embeddings, store them in like vector DB, and then like compare cosine similarities. That way, it helps like really fast lookups and like really highly recall. It helps if you have like custom built quantizer and embedding normalizers and all that kind of stuff. Now, on the infra side, like NUMA-aware pod scheduling, basically anything placing pods with the memory of with the awareness of memory and PCI locally to the GPU. This boosts like this really helps in the MATML operations we do, which is lots of like LLMs these days. That way, like the GPU sharing, it's like essentially enforced by like partitioning. Each tenants get its own isolated memory, model level throttling, and that will help you with the SLO like violations. Like that way, you have like more granularity and control over that. And then you should have like really fine grained telemetry, something like even like simple open telemetry, like custom extension trace for each request across all layers, basically ingress to logging. Just have telemetry across everything. That way everything is more visible. uh, Again, this is architecture for something like recommendation engine. It follows the similar flow, like ingestion, and then you have Kafka in between instead of the gateway or whatever, and then you have Flink where you do the enrichment, and then you store everything in Redis. Inference pods, we try to have like something like ONX runtime, and then each model like always re-rank them, like a re-ranking layer that includes like business rules and if possible feedback loops from back. And then if something like say a recommendation engine, it would need like lots of parallelization weights. So re-rank them all the time from there. That way, like these models are not like very like constant or anything. Yeah. And then the caching layer, like the response layer always cache them. Something like anything would like Fastly or like edge inference fallbacks that would like really help. So this way we can like our like P50 latency should be like even 80 milliseconds end to end. So this is something like this is one possibility. Again, your mileage may vary, but like this really helps in most cases. Uh, uh, let's talk about like a little bit more intricate stuff. So how to ensure high availability for LLM serving and multi-tier routing. Uh, Basically, this high availability for LLMs is a non-negotiable requirement these days. So have regional replicas for LLM inference everywhere. Uh, and these clusters, you can coordinate them with like a service mesh that tracks like node, like health, and then like the loads and stuff. And then the inference clients have them like retry aware and then quorum based. Then they dynamically should select for the fastest healthy node from the set of regional endpoints, and then it should help for like a graceful failover in case of any partial outages or anything like that. And so traffic, it should be like, I mean, again, like depending on your requirement, if you have something like premium users and then product critical requests, or like freemium users, so have them like shaped in multiple tiers. That way you can use like custom flows for each of this, and internal tools and background jobs. Like basically you can have like something like a cold path models with relaxed SLOs to reduce pressure on the high performance pools. And you can use like something like a canary deployment, and then you can do like diff validation, and then even like doing like something like token by token divergence between old and new models, and then that way you can promote them to general availability more smoothly. So they essentially, I mean, like for the summary is basically you can have multi-tier traffic and then route them through like canary deployments and then things of that nature where you have more control. That way you can have high availability like achieved. Like dark launches are also preferred. That way you can run something silently behind the scenes, and then there's like synthetic traffic, and that way you can evaluate all this stuff before actually uh, pushing it to product, and then have some like, I mean, some product regression risk. Like so I think we're nearing the last of it. Like, so let's go through some of the other tips. So the this is more on the safeguard side. Like how would you uh, make sure that your infra is uh, assured? So one thing that really helps is like pre-warming GPU nodes based on time of day load forecasts. So these can be like these forecasts. You can have like some simple ARIMA models. Like you can essentially guess some level of with some level of accuracy where the spikes would be, and then have them pre-warm. That way we don't have like cold starts or anything like that. Uh, and like you should have some logic to safely drain nodes without interrupting in-flight inference. So especially these days, like with the long context LLM calls, we want to have some logic to essentially safely drain nodes. Like if there is some interrupting in-flight ones, that really helps. Yeah, how like really anomaly detection with informatics, like real time. So this really helps. This would go something like, you know, rising Q lens, node pressure, memory leaks. They all should help with you. Next, one of the proactive rollback is something that like really helps. So like anything statistical significant degradation in latency or accuracy after a new model deploy, system should automatically roll back. Uh, like this obviously helps like outages and stuff. Also, rate limiting, you should have like a global rate limiting sync using something like etcd, and then Gauss shipments for fault tolerance. Future proofing AI architecture, like you can have something like a these just things keep changing fast. So you want to have something like as much as abstraction as possible. You can have like model as service abstraction, and then have cloud neutral deployment wrappers. This really helps. That way, I don't know, in case your business requirements change, the cost of the providers change, you can always change. And then like you can have on-device inference edge sync or private relay queues. That way you don't have to you don't get affected with the cloud deployments per se. So to summarize all of this, just to wrap up the presentation, we want to treat elasticity and then resilience and observability as first-class citizens. Have clear abstraction layers. You should like at the data model, and then modeling layer, and then orchestration, monitoring. So just remember, like the whole thing about MLOps, like we should be mostly about velocity. It's not about tooling. It's about culture. Like I mean, like you should be experimenting a lot. They should be reproducible. Failure should be traceable. Every release should be measurable. When that's true, I think like we can move really fast. Like especially with these days, with the like changing AI architectures and everything, this is the way to go. And have like really good calculators. Those costs don't run cheap. Um, okay, thank you. That's the end of the presentation.